Yeah, fine. So we will start the demonstration of this ADC circuit. So let me just show you what the circuit we have. So this is the IC. Let me just take both of them side by side. So this is my IC and this is my circuit. Let me write the circuit also side by side. So what I have is this is ADC using 0808 IC. As you can see, it has got 28 pins. Please write down the circuit, whatever. This is a 28 pin IC, out of which there are 8 inputs. So this is IN02 or IN02, IN7. There are 8 possible inputs, and then I have a start signal. There is a clock and there is a EOC signal. So these are the inputs, this is an output, and along with that I have one more input called as ALE. Here this ALE is for latching the address. This is for latching the address. So what I do is this is ALE, this is again an input, and I have a 3-bit address line, which is A, B, C. Why we require this 3-bit address line? To select one of the input. So we have the selection as ABC. So A happens to be the LSB part. If it is 000, I will be selecting the selected input, the selected analog input would be I0. If it is 111, so I will be selecting I7. Correct? When I say, okay, let me say IN0 and IN7. Is that fine? Is it visible? Over now? Yeah. So depending on the line, depending on the values of ABC, I will be selecting the corresponding input. Correct? Hello. And I will have a 8-bit digital output. So this is digital output. So I am writing it as 8-bit. So this is a 8-bit line. And along with this, I have an output enable line. Can you see that? That is over here. Can you see there is an output enable? Pin number 9. So this is output enable means, okay, I will, if it is made high, then I can able to read the output. Correct? And of course, along with this, I have a VCC line. I have a V reference line also. I will be connecting it to 5 volt. And there is a minus V reference. Which I will ground it. And there is a ground. So there is a ground line. Here, this minus V reference is grounded. You may have to note down this circuit also, because we may be using this when you are actually coming to SIK department. You are supposed to do the experiment. So there is a ground pin which is grounded. There is a V reference and VCC which are connected to 5 volt, and there is a minus V reference line, that is a pin which is grounded here. This is IN02, IN7. There are 8 inputs. So I have 8 analog inputs here, and of course I have 8 digital output. So out of 8 analog inputs, you can select any one of them depending on the select line. Correct? Hello. One of you unmute. Now I can be unmuted. Okay, now the circuit, what we do now is we will short this ALE and start and give to W2. We will short ALE and W2, we will short that and give it to channel 2 of your waveguide. And for this clock, let us use channel 1. So channel 1 is giving the clock, channel 2 is actually giving the start signal, which is also shorted with ALE. And this is always connected to plus 5 volt. What does it mean if we connecting always this to plus 5 volt? This means that you are enabling the output pin all the time. So you could be able to read the output pin whenever your EOC goes from low to high, whenever it goes from low to high. So this output enable is made high so that you can able to read the output at any point of time once your conversion is over. Correct? Hello? Okay. Now let us consider this is my clock. This is my clock, and I'll give a startup conversion like this. This is your clock. This is start bar ALE line, correct? And I'll have a ABC and have a ABC. It can be 000, it can be 001, or it can be anything. Fine. And then I have a EOC signal and have EOC signal, which is okay. Whenever your start signal goes low, this EOC will go down and then it again becomes high. So from here to here is your conversion time. Correct? That's what we saw here. That's what we saw yesterday. Is this the thing what we saw yesterday? Let me just go down here. Where is that? Let me just go to that voice issue. I'm just holding my mobile close to me. I think it's fine. Let me just hold it very close to. Okay, fine. Is this fine now here? There is a clock, there is a start signal, there is a ALE signal, both are shorted, and the address is given 000, whatever the value, and you will be giving the analog input, and you are giving, of course, this output enable is always made high. Instead of making high only when it is over, I am just making this always high, and there is a EOC signal which is an output coming from your ADC, which goes down during the conversion and again goes up. Correct? Come again?
Once the conversion is there, it will again go to high.
Of course, during the conversion time, EOC is 0. If EOC is 0 means it is still processing the conversion. So only when it goes from 0 to 1, it is the end of your conversion. So you can able to read from them. So let us see how we are implementing the same using the circuit which I showed yesterday. So let me just show you that circuit, whatever I have read up yesterday. Let me just bring the same circuit back to here. Of course, you will not be able to, this is the exact circuit what I have shown in the textbook. What I do is I will go to WaveGen and then try to see. Okay, let me just connect, share it. So I will be sharing. Where is WaveGen? Okay, let me connect the WaveGen. One second, it's opening now. Okay, WaveGen, where is WaveGen? Okay, let me close this. Okay, now it got connected. Let me share it. Okay, it's here. Can we now able to see this waveform window? Yeah, now as per the circuit diagram, we are supposed to use both the channels. One is for clock, other is for startup conversion. Correct? So clock should be, of course, both of them should be a square wave. You can see I'm giving a square wave, and since I want to have 0 to 5 volt, can you see the clock is usually of 0 to 5 volt? Can you see now it is -1 to 1? I will change this to 2.5 amplitude and offset also 2.5. Can you see now it has become 0 to 5? Is the amplitude of your input signal, clock signal, is going from 0 to 5? And I will make, of course, let me make the frequency of this as 100 kilohertz. The frequency is 100 kilohertz, correct, of the clock. And I have one more square wave for startup conversion. This is, okay, let us take it as 1 millisecond or 1 kilohertz. Let me again take it as 2.5 volt. And let this also be again 2.5 volt. So what is the point of making 2.5, 2.5?
So it will be starting from 0 going to
It is 0 to 5. And can you see what is the requirement of a clock like thing? So are you supposed to have something like this here? So do you want a clock which is of something like this? This is clock which is periodic, but can you see the startup conversion should be a single pulse and it should be there 0 for a long time. So how do we generate such type of signal? Now you can see this is 1 millisecond. Sorry, this is actually 10 microsecond. Why it is 10 microsecond? The frequency of the clock is 100 kilohertz. So for one period it is 10 microsecond. So what I do, this is 10 microsecond. Suppose if I want to get these pulses, after 100 pulses, after 100 clock cycles, if you want to get next pulse, what should be the clock frequency of this? What should be the frequency of? Now you can see what is 100 microsecond into 10 microsecond into 100 pulses. Is it actually equal to 1000 microsecond? Is this equal to 1 millisecond? If the timing is 1 millisecond, will I get one startup conversion for every 100 clock pulses? I will get it as so and so, correct? Just give me 1 minute time so that I can just fix this wire which is coming in my way. This is fine. Okay, this is what I have. Now I have to choose this frequency. I have to choose this frequency such that it gives a clock, it gives a pulse, and then it repeats after 1 millisecond. Then what should be this frequency? Does the time period should be 1 millisecond? So then the frequency is 1 kilohertz. Shall I take the duty cycle as hardly 5 or 10%? Only for a very small duration let it be high, for rest of the period let it be low. Why it should be let it be low means because I should take the address only once in 100 clock cycles. I'll tell you why you require 100 clock cycles. So my intention is whatever address you give, it will be considered only when ALE becomes high. So you are starting the signal and you are latching this address for every 100 clock pulses. Correct? Meaning, shall I go back to this and then shall I make it as 5%? So what does this actually mean? Does it mean that for every 100 pulses you are going to have a pulse of duration 0.5 millisecond or not 0.5 millisecond? What is 5% of 1 millisecond? It will be very less. correct? So what is actually this pulse width now? Is this pulse width? I'll just show it to people. What is the pulse width now? Is this actually 0.05 into 1 millisecond? So is it actually 0.05 millisecond? Is it actually 5 microsecond? It is 50, no? 50. It is 50 microsecond. So you will going to have a clock, or you are going to have a what is that? Start signal or ALE signal on for 50 microsecond. Correct? I'll turn on both of them. Okay. Before that, I want to see what all things I want to see here. Let me just go back to this. I want to see when is my start signal coming and when is my EOC is coming. After giving the start, I want to see what is after what time I get EOC. I'm not bothered about okay, what is my clock is. So what I do is I will connect this to C1. I will connect this to channel 1 of scope, this to channel 2 of the scope. So that I can see this waveform and this waveform. Getting the point? I want to see the start signal, how I am giving. I want to see this is going low and then it is again going high. So this is the point where I should able to read my output. Correct?
Yes, sir.
So this has been already done here. I'll go to my here. I will, of course, both the channels are there. Correct? You can see this is scope. Channel 1 is connected to start signal. Channel 2 is connected to what? EOC. And along with that, I want to see the digital output. Static IOs. So this 0 to 7. 0 to 7 are the digital outputs. This is LSB and this is MSB. Correct?
Yes, sir.
And you need to have 3 select lines ABC. This is those 3 inputs. This is channel A, that is input A. This is input B. This is input C. See now it is 0, 0, 0. I can change it to whatever the value. This is LSB, this is MSB. If I make it 1, 1, 1, I will be selecting some voltage. If it is 1, 0, 0, it is some other input voltage. Correct?
Yes, sir.
And to this pin number 15, I am connecting EOC again so that I can see the LED blinking. So what is this pin number 15 is? Pin number 15 is actually this. So pin number 15 is this one. So whenever it goes low, LED is going off. Whenever it goes high, LED will turn on. It is connected to both channel 2 of the scope as well as to pin number 15 of your static IO. To visualize, what we are doing is we are connecting the start signal to channel 1 of the scope. This is to channel 2 of the scope and this is to pin number 15 of static IO, and these 8 outputs are connected to where? 0 to 7. And this ABC are connected to pin number 8, 9, 10 of your scope. See here? Sorry, of your static IO. Now the question is, how do I give different inputs? How do I give different inputs? Maybe in the morning I have shared you one circuit, no? Did I share you some circuit with 7 resistors? So those are these resistors. Can you see these resistors here? These are the resistors from which I am getting the DC voltage to. These are, there are 8 different, can you see those 8 inputs there? So can you see there are, this is 1, 2, 3, 4, 5, 6, 7. This is ground, this is VCC, this is 1. Of course, I have one voltage here, other one here, this is this, this is this, this is this, and this, this, this. You can see this is I0. I1, I2, I3, I4, I5, I6, I7. All these inputs are connected to IN0 to IN7. Correct? Why I ask you people to find the digital equivalent of it? So I think some of you might have found the digital equivalent of those voltages. Can somebody give me? I have the values here. So what I do is I will just write. Okay, this is I7. This is I0, which is nothing but okay. This is V7, V0. Is V0 is equal to 0 volt? Is V1 is equal to 5 by 7 into 1? V1, that is this potential. Let me just write the circuit. Now this is bit involved. You need to get concentrated when I'm explaining something. This is same resistance RRR, maybe 1K or I don't know how much is the value. I think it is 1K. 1, 2, 3, 4, 5, 6, 7. This is grounded. This is 5 volt. This is 1. This is 1. This is also 1. This is R. So this is ground. This is V0. This is V1. So what is the voltage here? Is this actually 5 by 7 R into R? Correct? How much is the voltage here? Is it 5 by 7 into 2? Is it 5 by 7 into 3? Is it 5 by 7 into 4? Is it 5 by 7 into 5? Is it 5 by 7 into 6? Is it 5? So can I write the voltages as 0 volt, 0.714 and 1.428, 2.142, 2.856, 3.571, 4.285 and 5. Correct? These are the different analog input voltages. Correct?
Yes, sir.
So I can select 5 volt if ABC is 111.
Is equal to 1, 1.
Correct?
Yes, sir.
Now if it is 0, 0, 0, I will be selecting this. If it is 0, 0, 1, the analog input voltage is this. If it is 0, 1, 0, it is this. If it is 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0.
1, 0.
Correct?
1, 1. Yes, sir.
I wanted you people to find what is the binary equivalent 8-bit for these analog inputs taking V references 5 volts. I hope some of you might have found out.
Yes, sir.
Yes, let me write it in a different color.
Got it.
Of course, for this it is 111.
Yes, sir.
All the bits are 111. 1, 2, 3, 4, 5, 6, 7, 8. Correct? For this it is all zeros. Correct? Now, I am just truncating it to just whatever number I get. So, shall I write the decimal equivalent I will get? So, is it 219.4?
Yes, sir. 219.
And is it 182.8? Is it 146.2? Is it 109.7? Is this 73.1? Is it 36.55? Is it 0?
Yes, sir.
Now, what are the binary equivalent of 36? Okay, let us truncate it to 36, 73, 109, 146, 182 and 219. Let us truncate it to some. Let us not take 0.5 LSB. You can take either 0.5 LSB or you can just truncate it to the nearest possible. Is it, I think, just give me 1 minute. Sorry. ಸರಿ ಹಾಂ ಸರಿ ಸರಿ ಸರ್ ನೋಡ್ತೀನಿ ಹಾಂ ಓಕೆ ಕಮ್ಯುನಿಕೇಷನ್ ಬಂದಿಲ್ಲ ಇದೊಂದು ಸರಿ ಸರಿ ಸರ್ ಓಕೆ ಓಕೆ ಸರ್ ಎರಡನ್ನೂ ಮಾಡ್ತೀನಿ ಸರ್ ಓಕೆ ಥ್ಯಾಂಕ್ ಯು Just a minute. Okay, now what is 36 actually? Is it actually 0, 0, 1, 0, 0, 1, 0, 0? Hello? Hello? Hello, am I audible? Hello? Am I audible? Hello?
Yes, now you're audible.
Yeah. How about 73? What is 73? Shall I write it as 0, 1, 0, 0, 1, 0, 0, 1? Correct? I just ask people to just do it, okay, so that I can save some time. Is hello?
That is 0, 1, 1, 0.
0, 1, 1, 0,
Yes, sir.
1, 1, 0, 1. Correct?
1, 1. Yes, sir.
Is 145 is 1, 0, 0, 1, 0, 0, 0, 1.
0, 0, 1. Yes, sir.
And 182 is 1, 0, 1, 1, 0, 1, 1, 0.
1, 1, 0.
Correct? Then it is 1, 1, 0, 1, 1, 0,
1, 1,
1, 1.
0, 1, 1.
Correct?
Yes, sir.
Now these are all the expected output voltages for these inputs because they have been actually given in my circuit. So this is what is the circuit is. What we'll do is we'll just demonstrate or verify what are the actual values. So what I'll do, let me also give the power supply. So I'm using the same power supply which is over here. Where is supply? This is supply. Okay, I will use 5 volt here. Negative is not required. I will run it. I will run all of them. I will run this also. Now you can see there is something coming over here. Let me just make some adjustments. I'll just slightly move it up. I'll just make this also 2 volt per division. I'll just move this slightly up. I will move this slightly down so that everything is clear. Let me just move it by 5 volt.
Yes, sir.
See now? What is there in channel 1? Let me stop it. This is startup conversion. Startup conversion. Startup conversion is given, and you can see this is my EOC. Once the start is given here, so once it comes down, okay, as soon as your start goes up here, can you see the conversion has started? Can you see the EOC has become 0? EOC, this is EOC. So channel 2 is EOC.
Yes, sir.
So the conversion has started because you have said you start the conversion. This is startup conversion.
Yes, sir.
Unless startup conversion is given, prior to this, can you see EOC is at high? EOC high means it is not converting. Now, when startup conversion goes high, it is starting the conversion. The actual conversion starts from the actual time is valid once your startup conversion goes low. Now,
Yes, sir.
if you can see in this, where is that? See here, is the startup conversion valid from here to here? See here, startup conversion once your, end of conversion is valid from the point where your start goes low to the point where your EOC goes high. Correct?
Yes, sir.
We just go to waveform here. This is the point where your start is going low?
Yes, sir.
So what I'll do, I will take a cursor and I'll place both of them, one normal and one delta, Shall I keep it from here till this point?
And yes, sir.
This is my conversion time.
Yes, sir.
Can you see the conversion time is almost 68 microsecond? Suppose if I just slightly zoom it and then try to properly measure it. Okay, is it somewhere close to that? 68 microsecond? Correct?
Yes, sir.
So this is how do you measure the time, conversion time. Let us see why it is 68 microsecond or why it is 680 microsecond or not. Can you see now the conversion time is 686 microsecond? Hello.
Yes, sir.
Does the conversion time depend on the frequency?
Yes, sir.
Yes, it depends on. So for 100 kilohertz signal clock frequency, the conversion time is 686 microsecond. Correct? Shall we just go back to static I want try to see what the output? So what I'll do, I'll start from 0, 0, 0. See, when the input is, when the select line is 0, 0, 0, which input you are selecting? It is I in 0.
The first input I 0. Yes, sir.
Is that input voltage is 0 volt? Ground? V0. V0 is 0, no? Hello? 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 Am I audible? Hello? Okay, can you see this is blinking? Pin number 15 blinking is, it is purely because of this type of going low and high. Can you see this is going low and high sometime? That is being reflected here, correct? Now if I make A as 1, what is the output you are expecting? Can you see, are you getting almost the same output except this LSB is blinking? Suppose if I stop it, if I stop this static IO, can you see there is one LSB error? Can you able to see this is what you expect was 0, 0, 1, then 0, 0, then it was 1, 0, 0 expected. Can you see 1 is coming over here? So actually, what was the what was the exact output? It was 36.55. It is actually now 37. Is it actually now 37? Can you see? Is it a half LSB error? Instead of 36.5, we are getting 37. Whatever we represented was 36. So we underestimated half LSB. Now it's actually 37. Correct? Then shall we go to next? Hello. I will make this 1. I'll make this 0. Can you see now? I will make this. Can you see now? Is it 100% same output? Is it 0, 1, 0, 0, 1, 0, 0, 1? You just compare your value that you expected and how much you're getting. Is it the same thing? Can you see it is blinking again all the time? Blinking means you are getting the EOC keep on happening. Because you are giving startup conversion repeatedly, no? Using the clock, using that pulse. Now, if I make it 3, how much is expected? Can you see here it is 0, 1, 1, 0, 1, 1, 0, 1? Is it there? There is no error at all. There is no error at all. To be very frank, it would have been 110. Correct? There is a 0.7. but we set it as 109. So there is a half plus or minus half LSB error is there in this ADC. If you see the data sheet, there is an error of plus or minus half LSB. Shall we go to 100? Go to this 100. See, is it there? Is it 1001 0001? And shall we make it as 010? Is it almost there? Almost perfect?
Yes, sir.
But of course, you have a 0.8 LSB error. Next one is, I'll make this 0, I'll make this 1. Are you there? 110, 110, 11. If I make all of them 1,
Yes, sir.
can you see all of them are 1? This is we're not doing any magic here. We are actually conducting the experiment using this IC. Can you see this circuit is there? This is actually running now. So don't think that I'm just showing some which is already recorded. This is live now. Now you can see why it is taking 68 something 680 microseconds. Let me just go back to this. If you see the data sheet, what does your data sheet says is, let me just go to that data sheet specifications. Can you able to see this? This is a bit intense, but it is required. If you don't understand this much, then you cannot say that I learned something. Okay, where is that? Okay, can you see here conversion time? Well, conversion time conditions are if the frequency is 640 kilohertz, then it takes typically 100 microseconds. This IC will take typically 100 microseconds if the frequency is 640 kilohertz, meaning the number of cycles required for converting the analog to digital is 64 cycles. Getting the point? With a frequency of course you can write frequency is 640 kilohertz. 1 second. Hello. Is it fine? Hello. If the frequency of the clock is 640 kilohertz, the typical time taken is 100 microseconds. That is typical. Minimum it can take 90 and maximum it can take 116 microseconds. So typically 100 microseconds means how many cycles are required? It requires 64 cycles. Suppose if the frequency is 100 kilohertz, what is 100 kilohertz? One clock period is 10 microsecond. No? What is 10 microsecond into 64 cycles? It should be 640 microseconds. Correct? Can you see, were we getting 680 microsecond as the time, conversion time? I will just repeat it again. So what we'll do is we'll just make the clock frequency itself as 640 kilohertz. Shall we do that? Let me do the clock frequency as 640 kilohertz. Correct? What should be the time taken by the IC to give the output now? around 100 microsecond. Let us see how much it will take. Now the clock frequency has been intentionally made 640 kilohertz as per the data sheet, correct? Now I'll go to scope, I will run it now, I will stop now. So from where to where I should measure? I have to measure from here to this point. Are you there close to? Can you see there? Are you there at 107 microsecond? Suppose if I further zoom it down, zoom it in, just make sure that it is exactly there at that point. And then where is this? Shall I make it over here? Can you see it's almost there? Okay, this is how you can able to verify the things. I will stop it here and measure these timings. Now you got to know, okay, why it is taking that much time. As per data sheet, it should take 64 clock cycles. It is taking almost close to that typically. Actually, how much it is taking? It's actually taking, of course, it would have been 100 microsecond. It is actually taking slightly more than 64 clock cycles, but it is well within the limit. What was the limit? It can go up to 116 microsecond. Correct? Now, what we'll do is, we will see this blinking. We will see this blinking. So, shall we reduce the clock frequency to, what I'll do is, I will slightly adjust the timings such that for every 8 seconds, let me get the output. Suppose, okay, let me just try to calculate the values now. So try to scratch your mind, scratch your brain so that we'll get some timings. If the TC, that is time of conversion, if it needs to be 8 seconds, 64 clock cycles are required, correct? Am I correct? Clock cycles is equal to 8 seconds, correct? Then what is 1 clock cycle is equal to? 8 by 64, correct? How much is 8 by 64? Is it 1 by 8? Correct? What is 1 by 8 second in terms of hertz frequency? What is 1 by 8? Is it 0.125 hertz? Correct? Is it actually 125 millihertz? Meaning, if I apply a clock of 125 millihertz frequency, I will get after 8 seconds, I'll get the converted output, correct? So what I'll do, this is my clock frequency. How about my ALE? Shall I give my ALE after 10 seconds? Okay, what is the frequency for 10 seconds? Is it actually 0.1 hertz? Correct? 0.1 hertz, am I correct? Is that fine? Hertz. Okay, let me just change the timings here. Let me go to this. This is my wavegen. Shall I reduce the frequency to 125 millihertz? Correct? How about this? Shall I make it, if it is 1 hertz? If it is 1 hertz, 1 millisecond, I will make it. Okay. Okay, if I do it so, what happens? Let me just run it. Let me go to static. Let me go back to scope here. Can I just make this in terms of seconds? What's actually happening here? So am I giving my clock, start of conversion too much repeatedly? Because I have to give my, of course, this start of conversion is been given for every 1 second, which is not required, correct? I will go over here and then make it as 0.1, correct? If I make it as 0.1, if I now run it, this is your start of conversion. Okay, wait. Okay, let me just make it 5 seconds. Let me just go to this wavegen. This has become 1 hour 8 seconds. This pattern. There is something wrong here, no? So this would have been 125. Hello. For every 10 seconds I am giving, and if it has to happen at 8 seconds, 64 clock cycles. So this should be a bit higher frequency. I'll make it as 200 milliseconds. Let me see what happens now. Can you see now? Hello? Am I audible? Hello? Am I audible? Hello? What is the time of this one now? So I will take the normal one. Okay, let me delete all of them. One normal, one delta. I'll keep this one here and this here. Can you see the same thing happening here? You can see this is high. When it goes low, this will be low for this much period. So how much is the period now? It is 100 millisecond into 64. It will be for 6.4 seconds it will be low. For 6.4 seconds it will be low, then it goes high whenever your startup conversion goes. Now it is going low now, so this will be low for 6.4 seconds. You can actually count that. Hello. Okay, this way we can able to, of course, we can actually find out if the clock frequency, is 10 hertz, every clock will take 0.1 second. For 64 cycles it will take 6.4 seconds. We are giving startup conversion for every 10 second. For every 6.4, after every 6.4 second, we will get the output voltage. That's what we are seeing here. So that's what I am seeing in this static IO. You can see here, this is low, means it is converting. If I just make this something now, so now the conversion is happening corresponding to this particular input. I will get the output now. You can see once it goes low, this is changing. Okay.